So, as usual with me, a very long name and a very long title. Hopefully this will make a lot more sense when we get a few slides in. So, a little note to start. This is all sort of pre-commercial, so a lot of the geometries you'll see are fake, but the data you will see are real. Okay, that's the crucial thing. So the Barracuda simulations, it's sort of it's a testament to just how quick these things are, actually, that I had to say to my student, okay, they're not letting us show some of these systems, so can you mock up one that looks a bit like it and run the entire simulation in the next couple of days, please? And he said, yes, of course. And we now have these lovely, almost real but not quite simulations. So what I'm talking to you about today, there's three main parts. I'm going to introduce the plastic waste crisis, which I think we're all familiar with, but nonetheless it sets the scene a little bit with what I'm talking about for the rest of the presentation. I'm then going to talk a little bit about one of my pet topics, the importance of validation for numerical models, not just Barracuda, but DEM, CFD, DEM, and everything else beside. And I'm going to talk about how we have used positron emission particle tracking to validate Barracuda models, and then gone on to use these models to actually circle back to part one and start helping to address the plastic waste crisis. So a little bit of context and some figures. We produce as a society 400 million tons of plastic a year, okay? To put that into context, because these sort of big numbers tend to boggle the human mind, every year and a half we are producing the same weight of plastic as the weight of the entire human race, every year and a half. So this is a big problem. And 91% of this plastic to date has not been recycled. So it's a big, big problem. And of the 9% that is, I would say, quote unquote, recycled, most of this is actually what I call downcycled into low quality second life products. And I'll talk a bit more about low quality second life products at the moment. So currently in society, as I'm sure we'll all have noticed as we've seen plastic straws disappear from our McDonald's and whatnot, that there's this sort of idea that's very vogue at the moment that we should eliminate plastic, we should get rid of it. But is this really an achievable goal? And if it's achievable, is it sensible? Okay? Because plastic, there's a reason they're everywhere. They're both lightweight and durable, which is not a combination of things you find with many materials, which means they're not replaceable without some kind of a trade-off. So the question is, when we're talking about eliminating plastics, could the cure be worse than the disease? Because if you replace plastic with glass or metal, there's going to be increased transport costs. If we replace things with paper, we're losing durability. If we don't plastic wrap foods, we're going to increase food waste, which in Europe at least is actually a bigger driver of global warming than plastics. If we replace things with glass or other fragile materials, are we going to have increased losses? And if we replace car and plane and train parts with non-plastic materials, are we not going to reduce efficiency? So what I'm trying to say is a sort of a good example here. I'll rush through this a bit because it's only a short presentation, but one of the striking things that I learned about a recent endeavor by a company who I will not name to replace their plastic bottles with glass bottles, what they found out was when they did the analysis and all the losses they had with extra fuel to transport glass, extra waste with broken bottles, it's actually more environmentally friendly just to use plastic and throw it away than it is to try and recycle glass sometimes. But I'm not advocating using plastic and throwing it away. What I'm advocating is maybe we can find a third way. Maybe removing plastic is not the solution. Maybe recycling plastic is the solution. And again, the question I get a lot when I start talking about this kind of thing is, well, we do recycle plastic. There's a bin at my local shop that I can put a plastic bottle in, so it must be recycled. And what we picture in our heads is I take a nice clean plastic bottle, well, a nice used plastic bottle, put it in my recycling bin, and I get another plastic bottle out, okay? This, in the vast majority of our 9% of plastic that is recycled, is not what actually happens. What actually happens is you take your plastic bottle and it's turned into something like a carpet or a bin bag, because you can't, with conventional mechanical recycling, what you get out the other end is not sterile, so it can't legally be turned back into a plastic bottle. So when we're done with our carpet, well, we can't downcycle it any further. So what do? We throw it away. So effectively, most of the recycling we're doing is not recycling, it's just delaying landfill. So is there a better way? Of course, I wouldn't be giving this presentation if I didn't think there was a better way. So what we can do is take our bottle, chemically recycle it instead of mechanically recycle it, turn it back into something like the original crude oil from which it was made, and then get a nice virgin quality sterile plastic bottle back at the end, okay? And that is the goal of the company Recycling Technologies with whom I'm working, okay? So a little bit of an overview of this system. So this is Recycling Technologies' grand vision, okay? So you have this system, you have a thermal cracker unit where you feed plastics in, it's an oxygen-free environment, you crack the long-chain polymers into shorter-chain polymers, you then take them out, you refine them, you fractionate them, you distill them, and out the other end of this system, you can get, dependent on how you operate these two units here, you can get things like waxes, you can get things like clean, low-sulfur fuels, or you can go for the proper circular economy and you can get virgin quality plastic feedstocks, okay? So you're efficiently converting plastic waste into new plastics and anything else useful petrochemical-wise that you might want to. And by using fluidised bed technology, it allows large-scale processing. Now, one of the unique things about Recycling Technologies designs is it's a modular design. So each one of these units can be split up and loaded onto the back of a flatbed truck. Why is that important? What are the benefits of this modular design? It means it's easy and efficient to set up new plants. And this means you can actually, instead of having one big centralized plant in the center of your country or whatever, where you have to ship all your plastics to it and waste a bunch of fuel and pollute the environment that way, you can have a decentralized network of local plants, one in every sort of locality, one in every local region, minimize the transport cost and still get the benefits of chemical recycling. It also means it's accessible and affordable to developing countries. And this is important for a lot of reasons. So you can set these things up using minimal infrastructure. You don't need good roads. You don't need anything else like that. It means you can address it where the need is most pressing. So these are the countries suffering the most from the plastic waste crisis. So let's give them a way to monetize the plastic waste. If we look at plastic waste not as plastic waste, but instead we look at it as being crude oil in the making, then you can actually turn it into something valuable that you wouldn't want to throw away and dump in a landfill. So what's the problem? Sounds like we've got the perfect solution to the plastic waste crisis here. What are we waiting for? So it's a proven concept, but turning it into a commercial reality is not that easy. The reactor dynamics are not fully understood, so we need to, if we want to make this a commercially viable solution, we need to optimize these systems. But that's what the systems actually look like. So we have this nice idealized picture on the top, but how in the heck do you tell what the hydrodynamics inside that system actually look like? Well, there's two possibilities here, and we're trying to combine them both to make one even better possibility. You can either get an imaging technique that lets you see through steel, which luckily we have at the University of Birmingham, or you can model it, okay? And there are advantages and disadvantages to both of those approaches. So the seeing through steel one I was talking about, this is a technique called positron emission particle tracking. And to put it very briefly, effectively you take one of the particles you use in your fluidised bed, you make it radioactive and you track its motion through a system, and then by tracking the motion of this particle, if you're looking at something like a batch reactor, you can actually average the motion of this particle and get a full three-dimensional high-resolution image of the internal dynamics of this system. So velocities, densities, dispersion, mixing, anything that you want. And what this means is because out of this positron emission particle tracking, this PEPT, you get these full three-dimensional images, and then out of Barracuda, you get these beautiful three-dimensional images showing the dynamics of particles. You can use the former to validate the latter, okay? I'll talk about this a bit more in a few slides' time. So very briefly, this is my very beautiful model of a fluidised bed reactor. The particles are slightly oversized. So we take one of these particles, we make it radioactive, we put it in some kind of a positron camera, and because it's now a positron emitter, it's spitting out these pairs of gamma rays. They're highly penetrating, so they can penetrate several centimeters of steel. We detect them. We know that because it's from a positron annihilation, they must follow a straight line, so we can algorithmically reconstruct this straight line, and if we do that for enough pairs of gamma rays, we can locate our particle. And we tend to use tracers of the order of 10 to 100 million emissions per second, so we can actually locate this thing very, very rapidly, and we can follow its motion in great detail. We've imaged a wide variety of different systems using this technique, so we have a very good picture of its capabilities. So as I say, the pros, it gives us full three-dimensional dynamics. It can penetrate steel-walled systems, so we can look at real process equipment. But because of the nature of the tracking, it's difficult to image transient motion, and we don't get any direct information regarding stresses or chemical kinetics. So counterpoint that with something like Barracuda, which mercifully I don't have to describe at this particular conference. You get the full three-dimensional data, just like PEPT, but here you do get the transient motion, you can get the chemical kinetics, but the one but that we have with any numerical modeling technique, how do we know we can trust the output? Because any simulation method requires some kind of calibration, some kind of validation. So, as I say, we have these two options for seeing inside our industrial equipment, but individually, neither of them can give us the full picture. Okay? So what we're trying to do is combine the two. So we do some initial Barracuda models, and we use these to inform a set of experiments to do with PEPT. We then take the PEPT data, use this to calibrate the Barracuda model. We then take the Barracuda data and determine another set of experiments that weren't done in the first round that we can then use to validate the numerical model. And that means we get all the 3D dynamics, we get all the transient motion, we get the full information regarding chemical stresses, but we can trust it. Okay, and that's the crucial point. Okay, obviously with the chemistry we need to do a bit more analysis and TGA and whatnot, but the point is we've got this detailed PEPT data we can compare in great detail with our Barracuda data, so we can then, if we know we can trust our Barracuda model, we can then expand this out greatly, and instead of having to do a 2-hour experiment every time, we can populate the parameter space much more fully and much more efficiently with these numerical models. So the take-home point here is without strong validation, even the very best simulations can be inaccurate or at worst even unphysical. But with validation, we can trust them, we can expand them, we can use them to explore things in ways that using experiment alone are simply not possible. Okay? So when I say validation, what do I mean? Unfortunately, what a lot of people mean when they say validation is matching something like a pressure drop curve, or worse, just saying, well, that looks a bit like that, so I'm sure it's fine. And you joke, but I've seen this. I've reviewed research articles, so-called research articles, making claims like this. But as I said, both PEPT and Barracuda have this beautiful, rich, three-dimensional data. So in this particular case, validating a simulation of a fluidized bed, we compared 3 things that we know are crucial in the dynamics of a fluidized bed. So we looked at the flow patterns, we looked at the velocity distributions, and we looked at the turnover rates. So these things together tell us pretty much everything you need to know about the hydrodynamics of our beds. So the first thing we looked at was the flow velocity. So we get reasonable agreement between the measured and predicted expanded bed heights. We get a similar range of velocities. So obviously in this particular case, we're not looking at complete quantitative agreement, but we're getting the same ranges of velocities. And for the lower velocities, we get the same flow patterns. This is still a work in progress, but the point is you can see that this Barracuda model is painting a realistic picture of this PEPT experiment. That's just a little bit of a zoom in, so you can see here same qualitative velocities. The white patch there is just a lack of data from the PEPT, so that's just purely, we haven't got good enough statistics up there, so we're saying let's not plot any data. But the flow patterns are reproduced well, the ranges of velocities are reproduced well. The other thing we looked at was the circulation rate. So this is a distribution of circulation times, and what we see here, I should say dimensionless circulation times, but that doesn't matter particularly here because we're just comparing the PEPT in red to the MP-PIC Barracuda in blue. And this is where things, in my opinion, get extremely impressive. So the circulation time, which as we all know is a good indicator of how well our bed is mixing, we haven't just matched the mean circulation time, we've actually matched the whole distribution. And you can there see really strong quantitative agreement. We took it one further. We plotted the circulation rates as a function of this parameter here. And from the literature, we would expect this to scale linearly. Barracuda scales linearly, so we know it's physical. We know the results make sense. So these hexagons here, I should say, are Barracuda. The empty hexagons are Barracuda. The circles, filled circles are PEPT. And as you can see with these images, some of these we're getting, truly ridiculous levels of quantitative agreement. Some of them are a little bit off, but what I will say about that is looking at the data, the disagreement, the ones that don't agree so quantitatively well, the issue seems to be with a lack of decent statistics from the PEPT as opposed to being an issue with the Barracuda. So in my view, I think we can say this is a reasonably well validated model. So let's actually start applying it. So there's three main ways, in my opinion, you can apply a validated model in combination with some experiments. You can troubleshoot a system, you can optimize a system, or you can design an entirely new system. And all of these are things we're working on with Recycling Technologies at the moment. So this is still very much a work in progress. Designing an entire novel system is not an easy thing to do. But the other three I can give you some examples from. So I'm just picking a few little examples. As I say, I was asked to give a broad overview today as opposed to going into great technical detail, but if anybody does want to pick my brain on the technical detail, please say. So the system that RT use, it's a novel system. One of the really cool things about it is this two-reactor system where you have the thermal cracker, which we described here, but this is an oxygen-free environment, so it's quite hard to find a way to keep this hot. So what we do is we have a regenerator here, which is not an oxygen-free environment. We burn some hydrocarbon gases to heat up the particles that heat the bed, to then pump them through into the thermal cracker unit. And of course, it has some problems, because you've got one oxygen-free environment and you've got one oxygenated environment, which means if we get oxygen going into the oxygen-free environment, we're messing up our pyrolysis. Worse still, if we get hydrocarbon gases going into our oxygenated environment, we get explosions. Okay, so slippage is a big problem in this system. So one of the things we were tasked with by Recycling Technologies was to find out how to minimize the possibility of this slippage. So this is one of my fakey models that looks a bit like their real reactor, but not quite. So if you're planning on stealing anything from this, don't worry, it's a fake reactor. So the hydrocarbon gases should all be going out of the top of our system into the distillation columns, but they should not be going out of our outlet B, because if they do, then we're going to blow up our other unit, which is obviously not. I said this as a joke, but this almost happened a couple of times. And this one was actually turned out to be quite a simple one to solve, because the L valve, the standpipe that they had, can either be kept full or it can be kept empty. So we did a Barracuda model of it full of sand, a Barracuda model of it without sand, and we found that if you've got an empty L valve, like it was sometimes kept during operation, then you get quite a significant leakage of gas out. But simply fill the darn thing with sand, and all of a sudden you get very little. And this is a nice example of a serious problem being solved relatively quickly and simply. So moving on to sort of a brief example of optimization. So another question that they raised was with the L valve that actually pumps sand into the system, so pumping the heated sand into the cold system and vice versa. There was an open question as to, Is an L valve more efficient with a continuous flow of gas, or is it more efficient if you pulse gas? So by pulsing the gas instead of continuous flow, can you move the same volume of sand with less gas, thereby making the process more efficient? And if the latter, what's the best way to pulse the sand in order to optimize the efficiency? The answer to that is something I'm not allowed to tell you. But the point I'm trying to get across here is just some of the applications we've used Barracuda for with this particular company. The last one, and my personal sort of, what I think is the most interesting one, and the one with the most legs in the long term, is actually starting to improve the design, starting to really redesign these reactor units rather than just addressing specific problems. So if you've got Barracuda, you've got a detailed experimental method like PEPT, and you've got a 3D printer, you can do advanced rapid prototyping. And this is sort of, it's interesting. So we've talked a little bit about designing distributors already in an earlier talk, which I found fascinating. The ones I'm legally allowed to show you are not as exciting as those mushroom distributors, but we have had a go at a few that are slightly more crackers than what I'm showing here. But the point is, you can design a distributor. So this is one nozzle that forms part of a network. You can model it in Barracuda to look at the flow. You can then 3D print the ones that seem to be the most promising, and then you can actually perform PEPT experiments with the 3D printed models to see if they really do perform as well as you thought from the Barracuda model. The nice thing about this as well is obviously one of the limitations of PEPT is there is a limit to how big a system you can measure. So we're not going to be doing these 8-meter wide things. So the other powerful thing is you can take this to the next step, find something that works on a pilot scale model, and then expand it up using Barracuda to a full industrial scale model. And the one very last word I want to have here. So a lot of the examples I've shown are not in their own right particularly groundbreaking. But for those of you who follow Olympic cycling, you'll know that one of the things that the British team do that makes them really world-beating is they exploit this theory of marginal gains. So as a cyclist, you want to be really aerodynamic, right? So if you shave your legs, you make yourself a little bit more aerodynamic, right? But on its own, that's not going to be much. You might save sort of 0.01 of a second in a whole race. But you combine that with a dozen other things that save you 0.01 of a second, or 100, all of a sudden you're saving an entire second. And that could be the difference between winning a race and not even placing. And that's where I find things like Barracuda are extremely useful. So even though some of the examples I've shown may not be the most exciting thing in the world, do enough of them, as we are currently in the process of, and that could be the difference between a system that fails, that ultimately never makes it to market, and one that is commercially viable, or one that is world-beating. So to summarize, I think, well, plastic's a very big deal. We're working with industry using Barracuda and experimental methodologies together to make very strongly validated numerical models, and using these to try and take a big step towards solving the waste plastic crisis. So one very last thing, any questions you have are very welcome. If you're interested in PEPT, I'm going to shamelessly plug my book on the matter, and any questions you have are very welcome.